Hello, and welcome to this edition of Ask AIM, presented by AIM Solder. We want to bring our support and expertise to you, the customer. I have Tim O'Neill, the Director of Product Management for AIM Solder, here answering questions today. SAC305 is widely considered as the de facto standard for the SMT industry. Why was SAC305 chosen over the other alloy offerings?
Logan, the reason SAC305 was chosen was because it was compatible with the tin lead systems that were still in use, largely compatible, not entirely compatible. There were some concerns, but bismuth bearing alloys were discounted. Materials that had more toxic elements couldn't be considered. So you only have the periodic table of elements to draw from. So tin, silver, and copper made the most sense. That's the primary reason, was that it was compatible with what was currently in use and met the regulation requirements.
What are some of the drawbacks with the Sac family of alloys?
So SAC alloys have diversified. SAC meaning tin, silver, copper. Originally, the INEMI task force selected SAC307 as the replacement for 6337 tin lead. But that was quickly morphed into SAC305 because there was no real demonstrable benefit to the additional silver, SAC305 being 3% silver and 387 being 3.8% silver. And every 1/10 of a percent of silver can have a significant increase on raw material costs. Once the cost factor was considered, there was an effort to continue to drive the silver content down and still retain the benefit of silver in the alloy. Silver, generally speaking, improves wetting and lowers the melting temperature versus a tin copper material. So SAC305 became the standard for both surface mount and through-hole, but particularly in through-hole and wave soldering, alternative materials were investigated right away because the 3% silver significantly increased the materials cost in a wave solder operation. A solder pot fill went from a $5,000 expense to a $15,000 expense overnight. Materials on the floor became so valuable that there was theft risks. So there was a lot of advantages to keeping the silver content as low as possible. So there's been a diversification. SAC0307, SAC0807, all of the low and no silver alloys such as SN100C, K100LD, all of the SAC variants have a disadvantage in that when exposed to high temperature over an extended period of time, basically 100C, material suffers a loss of mechanical strength. So that is a fundamental issue with the SAC alloys that has been relatively recently discovered. I say relatively recent, within the last 3 to 5 years, it's become obvious. And there's a whole new second generation of lead-free alloys that's emerging that address that issue, particularly as harsh environments become more and more commonplace for electronics. So anything that gets hot, there's a risk that the solder joint's mechanical strength will degrade. And if it's in a high vibration environment, obviously there can be a premature failure. So those are the fundamental issues with SAC alloys: cost, and if it's not cost, it's degradation of mechanical reliability at higher temperature.
How does REL 61 compensate for SAC305's characteristics?
As I had mentioned earlier, there is a second wave of materials that are making their way into the marketplace. A couple of years ago, lead was essentially banished from the industry. And originally, I mentioned with the first question, the reason that SAC305 was selected to replace 6337 was that it was compatible with the 6337 system. Bismuth could not be used in a alloy if lead was still a potential material on the circuit board because it creates a ternary alloy with a very low melting temperature and very low reliability characteristics. So you couldn't have any lead with tin and bismuth. Otherwise, you'd end up with the significant reliability issue. But now that there is no lead in the system, if you want lead in your solder, you basically have to go back and add it back in because everything in the supply chain is now lead-free. bismuth has been revisited. So in the case of REL 61, it's a low silver bismuth bearing alloy. And the advantage to the material is that as it's low silver, it reduces cost. But as I mentioned earlier, silver enhances the wetting performance, and the bismuth enhances the wetting performance as well, and also negates the mechanical degradation or reduces the mechanical degradation problem. So REL 61 is a low cost as it's low silver. REL 61 wets as well as SAC305 and can in fact be run at lower temperatures than SAC305 because something else bismuth does is it lowers the melting temperature as well as improving fluidity or flow. REL 61 does not suffer the mechanical degradation with thermal aging. So REL 61 is the next generation. I think that you're going to see more and more alloys like REL 61 to address application-specific requirements. REL 61 would be a very suitable choice for a consumer electronic that suffers a relatively harsh environment. When we, for example, a laptop, laptops don't sit on a desk like a desktop. They get thrown in luggage, they get bounced around in a car. So you might want to retain some additional strength with the bismuth bearing material as that material won't degrade or lose mechanical strength.
I hope this gives you a quick summary of how AIM's REL 61 can improve your process. If you have more interest in exploring the use of REL 61 or additional alternative alloys, AIM Tech and Sales Support, along with AIM's website, aimsolder.com, are available as a guide in your education using these materials.